Hello everybody and welcome back to another CS Lightwork video. Today I am going to bring you guys an in-depth explanation and tutorial on the binary search algorithm. Now if you guys aren't familiar with what a binary search algorithm is, essentially it's a search algorithm that, given a data structure, a list, or an array, will return the index of the target value. So before we get into this, I do want to preface that binary search algorithm works for only sorted lists and arrays. So the data structure needs to be numerically sorted before we can implement this algorithm, or else it won't be fully functional. Now, if you guys aren't familiar with why we might use a binary search algorithm as opposed to something you might be familiar with like a linear search where we go through each element in the list to see if it's what we're looking for, it's because this is a more efficient way to search for a value as opposed to your linear search, as we're looking at a log O of n time complexity, which I'll explain later on in the video, as opposed to a linear time complexity. As well as this is more of an intermediate introduction to algorithms rather than what you might be used to with your bubble sorts and your linear search. But without further ado, let's get into the meat of the video. I'm going to be explaining to you guys how it works. Alright, so before we get into coding of the binary search algorithm, I'm going to give you guys an explanation into how the code is actually working and try to give you guys a grasp of understanding for the functionality of the algorithm. Now, if you're already familiar with the concept, feel free to skip ahead to the coding part of the video, but without further ado, I'm going to get into this explanation. So as I mentioned before, when we're looking at a binary search algorithm, it must be a sorted list and we are given a target value that we want to return the index for. Now, if this isn't making too much sense, don't worry, it'll slowly start to come together as I'm explaining it. So, for example, say let's just declare an array right here. Now we don't need to think of the specific numbers here even. Let's just say this is an array ending at index 5 and starting at index 0. So length of 6. Now this could be any list of sorted numbers, but essentially this is how the binary search algorithm works. So first we are given a target value. In this case it can be an arbitrary number. What we do initially, right away, is we split it down the middle. And you might be asking, CS Lightwork, how do we split it down the middle? We're looking at 5. Well, this is done through floor division. So in this case, when we do this, we would be given the index 2. So once we split it down the middle, this is what we do. We say, hey, is our target value smaller than the value at index 2? Or is it bigger than the value at index 2? Now this could be, again, any number, but think of it in index perspective. We're looking at that middle index and we're saying, hey, the value here, whatever value is here, is that bigger or smaller than our target? Now say that number is bigger. Our target is bigger than the value at our index 2 here. Well, then we know, because this is a sorted list, the target has to be within here, right? Because what we did is we split it down the middle on a sorted list and we said, okay, we know the target is bigger than that middle point. So now we know that the target has to be between index 2 and index 5. And we also know that it's not index 2 because we know it's bigger than index 2. So it's within index 3 and 5 inclusive. So essentially what we did here is we split it and checked which side it's on essentially. And now we know we continue the search on the according side. So in this case, it's great. The target is greater than the index 2 value. So we would look over here and we can essentially disregard this left side. But how do we do that? Well, here's the thing. At the beginning, what we did is we took index 0 and 5 and split it down the middle. Our left pointer will say our left side was at 0 and our right was at the end of the array, in this case 5. But now that we know, split down the middle, it's greater than, we essentially can move this left side right over here. So now we can set L to index value 2 because, hey, we know it's not before. So we can set it to index value 2. But wait, if you guys remember, and I'll just erase this for simplicity's sake. So if you guys remember, we checked value at index 2 and the target is bigger. So we can set our left to value 2 to index 2, but we don't actually need to check it. So essentially what we're doing here is we're setting left side is equal to the middle that we had plus 1. And this is because we're moving it to the right side and we don't need to check that middle value anymore. And then what do we do after that? Well, same thing. What we do is we take that middle again. And in this case, the floor division would come out to an index value 4. And guess what? The same thing. We say, hey, is the target bigger or smaller than the index 4 value? If it's bigger, we can move to the right, we can move that left, and if it's smaller, we'll move the right. But, see a slight work. What if it is index value 4? Well, perfect. That's our base case. We always need to make sure we check, hey, is that middle the value? And if it's not, then we do this right side, left side work. So, let's say for example's sake, our target was at index value 3, just for this example. Now when we're looking at this split, we have 2 to 5 and we set the middle to 4. If our index value is 3, that means in our sorted list, the value of the target is less than the value of index value 4. So what do? Again, we can disregard this, and instead of moving our left to the right, we move our right to the left. Now I know it's looking a little confusing, so I'll just clean this up for you guys over here. So now what we've done here, if I could get this to work, we've got rid of this left side here. We know it's between indexes 2 and 4. So now we have our right shifted to this index 4, and our left was always at the index 2. So what operation did we complete there? Well, we took our original right side, set it to the middle, right? But again, we checked right away if it's the middle value. So we don't need to set it to the middle. We could actually set it to the middle minus 1. And now, of course, if you run that same operation again, you're going to be left with value 3. And that would have to be the target. But wait, what if the target isn't value 3? Well, that's when you have your last case where you would say, hey, it's not in the list, we need to return something indicating that. But how do we do that? Well, simple. Say we set that middle point. When we check this code to say, hey, is the target equal to 3? It will say no because it's not on the list. Okay, so then is it bigger or smaller then? Now say for this example, it could be bigger or smaller. What's end up going to happen is either the right pointer is going to cross the left, or the other situation, the left pointer will cross the right. And again, I know this is a little messy, so bear with me. It'll make a lot more sense when we're recording it out, but that's what will happen if it's not in the list. So we'll have to keep that in mind and keep a case saying, hey, if our right crosses over our left crosses over our right, we need to stop. We need to return something saying, hey, it's not in the list. So again, briefly going over it, let's go into some numbers. Say we had a list going 1, let's say 4, 6, excuse the chicken scratches for handwriting, 8, 23, and 53. And let's just throw 75 in there very quickly, just to show you this works for any kind of length of arrays. How the merge sort would work, the binary search would work is, what we're doing is essentially we're splitting it down the middle here. So we would have right here, but of course this is a blank spot. Remember, floor division goes to the smallest one, so this we would be looking at this spot right here. And let's set our target to, let's say 6. So we would look here and we would say, hey, is 6 greater than 8 or less than 8? And guess what? It's less than. So we have our left and right here, and because our target is less than the current middle value we're looking at, we're just going to move this right over here, and now we're looking at something like this, where we have the left side to the middle, And we don't even need to include the 8 because we check the 8 right away. So essentially what we're doing is we're saying r is equal to so the index 8 is at, so in this case this would be 0, 1, 2, 3 minus 1, because we don't need to check that third index. So we could just close that off right here, and we're looking at right. And then the same way, it would go split down the middle, go to the value over here, and then we would say, hey, is it least, less, or greater, and so forth. And you can imagine eventually we'll be met at this point where all we'll have left is 6, and we'll be checking, is 6, the middle, equal to target? And the answer is yes. Now again, if that's a little confusing, don't worry. Once we get into the coding of it, it'll get much, much, much easier. Alright, so let's get into the coding bit of this. Now, if you guys aren't already familiar with the binary search algorithm, you'll know there's actually two ways to code it up. One is iteratively, where we use a while loop to continuously split it. And another way is we do it recursively, and that way you're calling back the binary search function with a different list each time. Now, I will show both of these in the video, and I'm going to be starting with the iteratively, but you guys might be asking, how come we'll do iterative, how come we'll do recursive? Well, in all honesty, it depends on not only, of course, your preference, but also the language you're using. Some languages do have a recursive depth limit in which you have a limit to how many recursive calls you can make. So for example, Python, ideally, you're going to do it the iterative way, using a while loop. But other languages, you might want to use the recursive way, but for this video's sake, I will be using both. But first off, we're going to start with the iterative way. Alright, so let's get into it. Here I have a blank binary search function declared. I'm passing this li, which is list, and then the target value we want. And then in main here, I have an example list, the same one we used in the whiteboard, and the target value, the same one we used in the whiteboard, and it's just going to print out what we return. So let's get into it. So first, as we mentioned, what the binary search algorithm does is it splits down the middle, then keeps splitting down the middle, right? You guys remember that picture? So we have to start it off, right? So we're going to start off by doing this. Excuse GitHub Copilot. Again, amazing thing, amazing tool to have, but I'm going to code it out here for you guys. So first, we want to declare that left pointer. And what's that going to be when we start off? Well, it's going to be 0. What's the right pointer going to be? That R side. Well, it's going to be the length of the list minus 1. And if you guys aren't sure why it's minus 1, well, it's because the length of this list here is 7, but the last index is 6 because it starts at 0, so that's where the minus 1 comes in. Alright, so now let's get into that iterative loop. So what condition do we have to follow? When do we know to stop? Other than if we hit the target, of course. Well, remember when I said at one point or another, if we don't have the value, left and right will cross over? Well, we know that our left value should always be smaller or the same as right. It should never be bigger, right? The left should be smaller or equal to. So that's exactly what we're going to do. While the left is less than or equal to the right, let's get into this algorithm. So now what are we going to do? Well, as I said, we need to define that midpoint. So what is that? Well, simply put, our mid, we'll call it mid, is going to be the left side plus the right side, and floor divided by 2 because we're looking at indexes, so we can't have decimals or floats or anything like that. So now we have that middle index. Now what do we do? Well, let's look at the obvious cases first. What if that middle index is the target? Well, let's put that in here. If the value of the middle index, so our list, the index value of the middle, is equal to the target value, return mid, because mid is an index, right? The value of mid will be list at mid, but mid is an index, and in this case, that's what we're looking for. Well, now what next? Well, what's the other possibilities? In this list, we split it down the middle, and what happens? Well, we split it down the middle, and we see, hey, it's smaller. The middle value is bigger than the target, so we need to look on the left. But what does that mean in code? Well, what we can do is, let's look at it. So we need another conditional statement to say this. Hey, maybe our middle element is not the target. In this case, our middle element is greater than our target. So what if the middle element, get ready for this one, is greater than the target? What do? Well, that's when we bring that right pointer to the middle, right? So what we're going to do here is simply say right is equal to mid. But remember what I said? We checked right here if that middle value is the target. So we don't need to check it again by setting right to the middle. So we can actually set right to mid -1. And keep in mind, left, right, and middle are all index values, not the value of the actual element. So now that we have this, what's that last case? Well, not in this example, but say we were looking for 23, where the middle value is actually smaller. Well, that's the only other case we can have, so we could just put that as else. And what do we do then? Well, if our value, after we split it down the middle, is greater than the middle, well, we need to move that left position to the middle. So again, it's going to be left is going to be equal to mid and +1 because we already checked the actual mid value. And now once we have this, we have our search algorithm done. But one more thing. What if we're looking for a value that didn't exist? It will finish the loop. They'll cross over and it will be out of the loop. Well, standard notation from what I've seen, typically we return -1, but we could return null, we could return anything you really wanted to, but this final return statement will only be affected if you do not have the element in your list, in your past list. The target doesn't exist. So now let's save that, and I'm just going to open a quick terminal to run this. Alright, so excuse the technical difficulties there. So now I'm going to run it in the CMD. Again, you guys can run it however you like to. I'm just doing it in the CMD for example. Now what we're going to do is now run this script, binary search.py. Now as you can see, it's going to print out 2 because I have the print statement returning whatever we return. So now let's run through this code really quickly. What is it really doing? Well, it's going to continuously loop until we either find the target or that left crosses over that right. Now in this case, the target value was 6, and as we can see, the index value is at 2. So this program is working correctly. Now say we passed a target that doesn't exist in the list, let's say 69. Let's just run that again, and as you can see, it's returning -1 because there is no value of 69. Now alternatively, I'll just put another value so you can see it one more time. This should return index 3. And as you can see, it returns 3. Now there is one more thing we should incorporate into a binary search, and that is to check if the list is actually not empty. And the reason we have to do this is because as much as you might assume, hey, I'm not going to call a search algorithm on an empty list, when it's up to different maybe user inputs or anything else like that, where the same person who might be calling the function didn't write the function or might assume that you have accounted for, the general rule is you need to account for an idea of the length of the list being empty. So all we have to do for this is if len of list is not equal to 0, or what we can do here is greater than 0, we run this entire code. Now I know this might seem a little, why would you need to do this, yada yada yada, but it's definitely a case you need to take into account when you're taking an input from which you don't control, right? Because you might not be the one calling your function. So as you can see, it will still run perfectly fine. Now, let's get into the recursive solution. Alright, so let's get into the recursive search version of the binary search algorithm. Here I've written a blank template and I've labeled the old one with IT so you guys can see the difference. And now before I even get started with this, there are 2 recursive versions I've seen. One where it still keeps the parameters list and target and it just passes a split list. Now for Python, that is the way to go, but because I'm trying to kind of give you guys the idea of how it would be implemented recursively, and like I said, other languages might prioritize recursiveness, not all other languages have some sort of list splitting function, array splitting function that's efficient to just keep calling and keep calling. So for this example, we're going to use the recursive binary search where in the parameters we pass the left and the right side. So here we're just going to add in left and right. And again, we're going to have to do this when we call the function. So again, why do we need to do this in the parameters? Well, simple. In the loop, when we look at the iterative version, in the loop, we are always modifying right or left, or we're returning, we're done. Now, in terms of a recursive function, you don't use a loop to continuously iterate and change. What you do is you continuously call the same function. So that's why we're adding in the left and right, because what we're going to do is instead of modifying left and right values, we're going to call the function again with modified left and right values. I know that might sound a little weird, but let's get into it and it'll be a little easier as we go. So first, what you will also have to do is where you're calling the search algorithm, you're going to have to pass in the left and right values. So I'm going to write these out to make it easier, but you could put them in right here. So the left is going to be 0, same as the first call as the previous function. And the right, again, it's going to be the same as the original statement right here. It's going to be the length of the list minus 1. And so we're going to pass those in. And now, it's sort of the same functionality. First, we need to cover the case to make sure that the left is not greater than the right, that we haven't gone over that sort of left crossing over the right. So as you can see here, we have a loop to implement. We have a loop that says, hey, if left is smaller, continue on going. But because we're not going through a loop here, actually at the beginning, what we're going to do is, hey, if left is greater than right, return -1 right away. That's our base case right there. So we're declaring that at the top right here, right? But otherwise, let's continue on. Now what we're going to do is make our mid. What we're going to do is the same way we declared it before. Mid is left plus right, floor division 2. And then we're going to look at the same old cases. So if the list element at index mid is the target, return mid, right? Same thing. Then we need to look at that second case. Else if the list element at the mid index is bigger, we need to bring that if it's bigger, we need to bring that right pointer to the left. We need to bring it to the middle. So again, else if the list element at the middle is greater than the target, we're just going to set the right, as we did before, to middle -1, right? But we are not calling it again. So instead of making this kind of call, all we have to do is we're going to use return statements. So return, and I'll empty the parameters so you guys can see this. We're going to return and call the function again, and we're going to pass the same list. We're going to pass the same left because this is where we're modifying right. And instead of passing the same right, remember how here we set right is equal to mid -1? So here we can just pass mid -1, and then we can pass the same target. And then as you guys can probably catch on, the next statement is just going to be your else, the last case, and it's going to return another function call to the same function, but left is going to be the middle +1. It's the same thing as here, but instead of modifying variables, we're calling the function again with different variables. And essentially, this is all we have to do. Now, if we go into here, and I go bring out my compiler over here, all we have to do is run it, and as you can see, you will be given 3, the same way. Here we're calling the recursive algorithm, and it's giving back the same answer. Now, let's set the target back to value 6, so we'll say 6 right here, and this should return 2, and what do you know? Returning 2. And again, let's do something that doesn't exist, 69. Well, it's going to see in its first statement and return -1. Now, I know this went a little fast and there's a lot of knowledge to take in here, but feel free to slow it down, rewind the video, ask any questions you need in the description below. I'm happy to help, but that pretty much sums it up for the binary search algorithms. As I mentioned before, the reason we use a binary search algorithm when possible is it is more efficient. In big O notation, we're looking at a log n time complexity instead of having linear time complexity you might have with, of course, a linear search. Here we can drastically slow down the run times and how long it takes, especially when dealing with bigger and bigger and bigger and bigger lists, right? But without further ado, that's the conclusion of the video. Thank you guys so much for watching. I hope this helped you guys out. Again, any feedback, feel free to leave below. Leave a like if this helped you in any sort of way. Feel free to subscribe for more videos. But that's all. Take care.